Very pleasant morning to and all join here. Myself, Dr. V. Nirmala, Assistant Professor of Statistics, Department of Statistics, Sri Sharada College for Women, Autonomous, Salem. I am going to explain the topic birth and death process, which is from stochastic process syllabus. The syllabus is for 3rd BSc Statistics students. The third unit, the topic 1 is visual representation of states and transitions, birth and death process. Introduction. What is a stochastic process? A stochastic process is a collection of random variables indexed by time. The importance in modeling random systems, it models systems that evolve randomly over time. Birth and death process are a special case where the system changes states by +1 is birth or -1 is death. The Markov process recap. The definition of Markov process is the memoryless property. The Markov process satisfies the memoryless property, which it can be represented in this equation. Probability of xt, t is the time, xt plus 1, which is j, by xt is equal to I, xt minus 1, which is going up to x naught. It can be equal to probability of xt plus 1, which is j, by xt is equal to I, probability of xt plus 1, which is j. The mid value xt is equal to I, xt minus 1. It is going up to x naught. So it will be equal to probability of xt plus 1 is j, by mid value of xt is equal to 1 into probability of xt plus 1 is equal to j, by divided by xt is equal to I, xt minus 1, which is going on up to x naught. It will be equal to probability of x t plus 1 is j, by xt is equal to I. The transition probabilities depends only on the current state. What is birth and death process? A special type of Markov process. Only adjacent transition, birth is equal to +1, death is equal to -1. A Markov process which transitions only be neighboring state. So state space is non-negative integers. The process can only move from states n to n plus 1, which is birth, or n minus 1, which is death. Real life examples. In this slide, I have mentioned 3 types of real time examples of birth death process in stochastic process. The population models. Organism reproduce, birth or die. Queuing system, customers arrive, birth and or served, death. Epidemics, infection spread, birth and recovery, death. Transition diagram. Visual representation of states and transitions. The diagram will states as nodes. Here arrow, the lambda n can be represented from the state n to n plus 1. Mu n from the state, the diagram n to n minus 1. The transition rates, birth rate lambda n, death rate mu n, depends on the current state. So lambda n birth rate of transition from n to n plus 1. Mu n is the death rate, the rate from transitions n to n minus 1. So both may depends on n. Infinitesimal generator matrix. Here structure of Q matrix for birth death process. Triangular form, the matrix Q or G shows transition rates. Q is equal to lambda naught which is going up to mu 1, lambda 1 plus mu 1, lambda 10 which is going to mu 2, then lambda 2 plus mu 2 by into lambda 2. The matrix can be arranged like this in row and column wise. Q is equal to begin B matrix. So lambda naught and lambda naught it can be going on in row and column wise. So we can write mu2 lambda 2 by mu2, and lambda 2 and mu can be written as minus lambda naught mu 10, such that lambda naught minus lambda 1 plus mu 1. So mu2 is can be represent 0 lambda 1 minus lambda 2 plus mu 2. It can be expressed as 0 0 lambda 2, which is going on in generated matrix. Kolmogorov forward equation. Derivation and explanation of Kolmogorov forward equation. Describe how probabilities evolve over time. Here t represent the time. So lambda n minus 1 p n minus 1 of t plus mu n plus 1 p n plus 1 of t minus lambda n plus mu n into p of n of t fraction of d p n of t dt is equal to lambda n minus 1 probability of n minus 1 of t plus mu n plus 1 into p of n plus 1 of t lambda n plus mu n into p of n of t dt. So it will be equal to lambda n minus 1 p n minus 1 of t plus mu n plus 1 p n plus 1 of t minus lambda n plus mu n into p of p n of t. So the Kolmogorov backward equation derives using backward Chapman-Kolmogorov equations useful for computing first passage probability and expected times. The time depends probabilities Pn of t can be expressed probability of being in state n at time t. How they evolve over time. Define Pn of t is equal to P of x of t is equal to n. Pn of t, P of x of t is equal to n. Pn of t is equal to Px of t is equal to n. Use forward equations to solve for them. Requires initial conditions Pn of 0, Pn of 0 into Pn of 0. Steady state behavior, limiting distributions, conditions for equilibrium. If the system reaches a stable distribution, limit tends to infinity, Pn of t can be written as pi n of limit t by to infinity. Pn of t can be written as pi and t tends to plus infinity, limits n of t can be written as pi n. Exist under certain conditions, for example, finite birth or death rates. The stationary distribution. The stationary distribution can pi n expressions. The normalization condition can be summation xn is equal to 1. The detailed balance equation pi n lambda n, which is equal to pi of n plus 1 mu of n plus 1. Solving for pi n recursively. Example M1Q can be considered here. Arrival rate lambda, service rate mu, states the number of customers. Deriving steady state distribution, the single server queue can be represent the Poisson distribution, the rate mu, and the exponential distribution rate mu state the number of customers in system. The arrivals can be lambda and service can be mu. The probability of n customers pi n is equal to 1 minus rho power n, where rho is equal to lambda by mu. Here considering the geometrical distribution, rho is equal to lambda by mu, rho is equal to lambda by mu can be written as lambda by mu. Steady state lambda n is equal to 1 minus p into n by pi n, which is equal to 1 minus rho to the power of n by n, which can be written as 1 minus p power Pn. Exist of P less than 1, row less than 1, row less than 1 is the range for probability of n customers. Mean and variance of expected number of individuals or customers, variance of population size. For MM1 model, expected number can be expressed the expectation of n is equal to row 1, row by math bb E and n. The fraction of row 1 minus row expression of n is equal to 1 minus row. The variance can be written as variance of n row into 1 minus row 2. It can be equal to 1 minus row into 2p. The extinctions probability. What is extinctions? The conditions under which extinctions occurs, the probability that systems reaches state 0 eventually if death denominates birth. Example, lambda n less than mu n, lambda n less than mu n, lambda n less than mu n. So the extension is certain, the observing state. Here, when the state 0 is observing, for example, extinction, state from which the system cannot leave. If mu naught is equal to 0, mu 0, which can be written as 0, then 0 is observing. Common in extinction models. Time to extinction, expected time until absorption, method to compute it, expected time to reach state 0, solved using recurrence relations or Laplace transforms. Birth only the process. Special case mu n is equal to 0. Just now we derived the previous slide. So explosive behavior, if mu n is equal to 0, mu n can be written as zeros for all n. The population growth without bound can be explosive. The death only the process. The special case lambda n is equal to 0. Convergence to 0 population. System always reaches to 0 eventually. So applications and summaries for birth, death, stochastic process, the population biology, queuing theory, epidemiology, and telecommunications. The biology, population growth and extinctions, queuing service systems, and epidemiology, spread and control of disease, telecommunication, packet traffic, and call centers. These are some applications of stochastic process. Here in this slide we will see the conclusion of this presentation. Key concept recap: the importance of birth death process and its real-time applications and its modeling. Birth death process models real-world dynamics simply and effectively. They are backbone of Markov process theory, applicable across many disciplines. So in this slide I have represent the reference book. You can use the author name Rose and Selden. The title of the book is Stochastic Process. The another book Markov Chains, which is good for students level. Norris J.R. the author name. Kindly refer these books for this topic. I have selected some notes from this book. Thank you for watching. Thank you all.